and it will form, it's the null generator of the horizon. So this is H plus. So we call this C0. And we call the previous one that manages to skip the strike box, call it C1. Okay. U is the affine parameter along strike box. V is the affine parameter along strike lines. So we're going to be interested in looking at the geodesic, at the distance between two neighboring null rays, between C0 and C1. So for that purpose, we look at the null ray C that goes through, it crosses C1 and it crosses C0. This is the affine parameter, we call it lambda, at lambda equals 0, it's when it crosses C0. And the value of the parameter lambda when it crosses C1, we call it lambda 1. So that's the setup. We use so this is spherically symmetric. And so by Birkhoff theorem, outside the star, Schwarzschild spacetime, outside the object. I call it object because at early times it's a star, and later on it's a black hole. Whether it's a black hole or a star, it's very symmetric, and so outside it, the space-time is the Schwarzschild space-time. So we used the equations for geodesics, no geodesics in Schwarzschild. And then we derived a relationship between U and lambda. So we saw that U is 2e lambda minus 4m log of lambda k1, where E is the energy of the geodesic. Okay, this is U. This is U lambda. This is the value of U along C. Okay, so E is the energy of the null geodesic C. M is the mass of the object. And Ky is K1 is some constant of integration which is less than 0. Because lambda is negative before it reaches the event horizon. As it approaches the event horizon, that's lambda approaches 0 from the left, this will diverge, and so this dominates over the constant term, the infinitesimal term. So I think that's as far as we did. Okay, so what's the affine parameter separation between C0 and C1 along C? What is the affine parameter separation between C0 and C1 along C?
zero, u of lambda 0 minus u of lambda 1.
No. Along C, what is the affine parameter?
Lambda.
Okay. So what's the difference in the values of lambda between these 2 points?
Is lambda 1.
It's lambda 1. Okay. Minus lambda 1 because lambda 1 is negative. So the affine parameter separation between C0 and C1 along C is lambda 0 is lambda 1, lambda 0 is 0. Okay, this is lambda 0. And so it's minus lambda 1. Okay. What is the affine parameter separation between C0 and C1 along square minus?
V0 minus 1.
Exactly. So the affine parameter, V is an affine parameter along square minus. This is a V equals V0. This is V equals V1. So the affine parameter separation between C0 and C1 along square minus is V0 minus V1. What is the affine parameter separation between C0 and C1 along sky close?
Is u1 minus u1 minus u0. The tree is lambda v. This is lambda of v1 minus u of v1 minus u of v0.
Well, what is U of V0?
U of v0 is
You don't even need to look at the notes. It's immediate from here.
lambda 0 minus u lambda 1.
What's the range of values of U? What is the range of values of U?
Minus plus n.
What's the value of U here?
Here is
Like,
minus infinity.
it's minus infinity. It's just the same as in flat space time. What's the value of u here?
Plus infinity.
Plus infinity. So what's the value? What's the geodesic? What's the final separation between Z0 and C1 along? It's kind of close. Infinity. Because it goes, it's like this that it's the value of u at lambda equals 0 minus the value of u at lambda equals lambda 1. But this value is finite. The value of u at lambda equals lambda 1 is finite. The value of u at lambda equals lambda 0 is infinite. Now it goes to infinite in this way. So we're going to get this in a minute. Is this clear? You're struggling.
Yeah. Lost.
Okay.
So,
Where are you lost?
I was thinking more like the part of the developments you made in the last class.
Sorry, which?
The development that you made in the last class
Which development?
of that expression.
This one.
I was thinking about it. Yeah.
Okay.
I have to read it somewhere.
I thought I derived it for you at the end of the.
A part of it.
I had a derived part. Okay. Null geodesics. Radial null geodesics. This is what we call dr star. So dr star plus minus dt equals 0. So u is r star, t minus r star, and v is t plus r star. So u plus constant and v plus constant correspond to radial null geodesics. And then the other bit is, I didn't do it in the lecture, but I did it for you at the end. Now, I'm going to get the signs wrong and everything. But you use the other Lagrange equations. So your Lagrangian is, so you're maximizing, so geodesics corresponds to maximizing g dot mu dx mu dx mu. Sorry, x dot mu d line. Okay, the dots are just derivative with respect to lambda. So geodesics are extremum of this Lagrangian, of this action with this Lagrangian. Sorry, what you said? No, not that.
That's
Just. So that's the geodesics. And then Euler graduations. Partial derivative of L with respect to x dot mu is equal to
T lambda.
oh yes, sorry. Thanks. So the Lagrangian is just a metric with dots instead of differentials. Spherical symmetry. Allows you to put everything at theta constant, and so you choose pi over 2. So this would be 0, and this would be 1. And now you use more symmetries. So it's Schwarzschild space-time, it's spherically symmetric. So it not only does not depend on the metric, does not depend on theta, it does not depend on phi. So you choose phi. I use var phi for the field. So Lagrangian does not depend. So Lagrangian is a function. The Lagrangian is a function of x mu and x nu dot. So that's what partial derivatives do. So it depends. The only coordinate on which it depends is r. Okay. So the dependence. So the Lagrangian, the dependence of phi 0. So that gives you a constant of motion. The symmetries give you a constant of motion. So that tells you that this is constant. Okay. Now you differentiate with respect to phi dot. Phi dot, so that's 2 r dot squared phi dot. Sorry, not r, right? There's no dot. Phi dot. Okay, so that tells you that phi dot is a constant divided by r squared. That constant is called it's the angular momentum. Okay. Axial symmetry gives you conservation of angular momentum. Now you do it for t. Again, the Lagrangian is independent of t. Static. That tells you that this is constant. And so this is minus 2f t dot. So that tells you that t dot is some constant divided by f. That constant, we call it E. It corresponds to the energy of the geodesic at the infinity. So these are the symmetry statistically gives you conservation of energy. So that's where dz comes from. So let's see. So right. So the dots. So this tells you that t is E. So let's see. So we're doing, so du d lambda is dt d lambda minus dr star d lambda. dt d lambda is t dot, so it's E over f. and dr star d lambda, dr star d lambda well, so dr star d lambda, you can write it as dr star dr d lambda. Dr star dr is 1 over f. And dr d lambda
because the radio they should satisfy that equation there. Minus f dt is equal to 1 of f dr.
I mean, I've written this in a very, I'm doing this more complicated than it is, in fact. So, in fact, dr star d lambda is dt d lambda, but we're looking at ingoing geodesics, so this must be minus dt d lambda. You're free to choose the sign here, plus or minus. So this really is minus 2 EF minus 2 dt d lambda, which is minus 2 EF. Sorry, minus plus 2 d lambda, 2 EF. And then so dr d lambda, so we're still, I want to integrate with respect to lambda, f depends on r, so I still want to get r as a function of lambda. So dr d lambda is dt minus dt dr d lambda is going to be minus f dt d lambda. F dt d lambda is e, so this is minus e. So r is minus e lambda plus some constant. At which free to choose that constant whichever way we want, but we've chosen the origin lambda so that it's equal to lambda is equal to 0 whenever it's crossing the event horizon. So whenever r is equal to 12. And now you can just integrate. Right? So now you've got, this is 2e 1 minus 2m over r. So that's 2e r minus 2m r. That's 2e r is 2m minus e lambda, and r minus 2m is minus e lambda. And you integrate this, and it gives you this. The creators of knowledge of geodesics and stars, so we can find them in many books, but that's a quick and easy variation. Okay, so apart from these geodesics, is this diagram clear? I mean, I'm not expecting a massive cheer for this. Is this clear? Is it? Yeah, David? Is it clear? Is it clear? Aula?
Yeah.
Okay. If things are not clear at some stage, just ask.
Just a dumb question there in the when you check or you can how you get the null geodesics from that integral.
From which integral?
When you take the extreme of g nu x dot mu.
Well, I've submitted that, which, I mean, no geodesics are just
Right.
just this. But you can do this for R, x mu for R.
I mean the integral. Isn't the integral of that integral 0 for null geodesics?
When you evaluate them on no geodesics, yeah, but you can't do that at this stage. You first of all have to extremize.
Okay.
Or differentiating, right? We have to differentiate first. Make the real equal to. You can't just put the value before you differentiate. Okay. Now, we want to relate, so we have the affine parameter here, we have the affine parameter along here, and we want to relate these two. Now, you can show, this is mentioned in Wall's book and in many books, although I haven't seen a clear derivation of the following, I have to say. But it can be shown. That the way so the relationship between the affine parameter separation can only be linear between here and here.
Sorry. Can you repeat?
So I'm just saying in words what I've written here as an equation. The relationship between the affine parameter separation between two neighboring null geodesics that affine parameter separation evaluated at 2 points at 2 different stages among those null geodesics is only, the relationship is only linear. The growth or the decrease in the affine parameter separation can only be linear. So heuristically, it's quite trivial. The details, I haven't seen them anywhere. So heuristically, I'll just give you the heuristics. But if you can find the details somewhere, I'd like to see it. Heuristically, we're looking, so as I say, a affine parameter means you've got, affine parameter separation means you have a geodesic crossing through the two of them, and you look at the affine parameter interval along that geodesic between those two, between the crossing of the two with the two other geodesics. So as I say, sky minus, you look at the affine parameter along here, and the value of the difference in the affine parameter between these 2 points. And you can do this anywhere. You can do it here. Look at the null geodesic going crossing the 2 of them. And what is the interval in the affine parameter along this geodesic between these 2 points? And that's exactly what we've done here. We're looking at a null geodesic going across, crossing the 2 C0 and C1, those 2 other null geodesics. And we want to know what the affine parameter interval along this geodesic is between the crossing of the 2 other geodesics. So like we said, this is in here, it's lambda 0 and lambda 1. In here, it's just P0 minus P1. You can do that here. We want to know, you can think of an null geodesic that's chi plus that's crossing these 2 neighboring null geodesics, C0 and C1, and you look at the affine parameter along this chi plus null geodesic as it crosses C0 and C1. And the affine parameter, like as you said, it's infinite because the affine parameter is U. The affine parameter interval is infinite because the affine parameter U is infinite at this point and it's finite at this point. I'm just repeating for the second. Now, in order to relate the affine parameter separation between here and here, I'm appealing to a theorem or a calculation that tells you that the relationship between the affine parameter separation in 2 different stages must be linear. Okay, so let me just give you the heuristics. There's an equation that relates so there's the geodesic deviation equation that relates so chi is the separation vector. Okay, so this would be C0, C1, this is C, and chi is just the separation vector. The vector that goes between C0, between C1 and C0. And we want to relate this at 2 different points. C, let's call it C. I'm not even going to call it anything. So C0, okay, so along C1, let's see that the affine parameter is lambda bar. So lambda bar is equal to lambda bar is lambda bar is lambda bar initial here, and it's lambda bar final here. Okay, so then here this should be lambda bar. So this tells you, you choose your C1, and we want to know the geodesic define parameter separation between C1 and C0 at 2 different points, 2 different moments along C1. Okay, a moment lambda I and a moment lambda F. The separation is given by chi, the vector chi, joins C0 and C1. And this is as it varies along C1, where lambda bar is the define parameter along C1. So that's, I'm omitting the indices, that's why I'm just putting a tilde. I'm just doing heuristics here. So this is the Riemann tensor. There's indices. Okay, whatever. I can't remember which is which, but anyway, there's indices here. Okay, so this is the Riemann tensor. This is U. U is the 4 vector along C1. for velocity along C1. So this is this. Now the crucial point is that this is linear in chi. Okay. Now you can rewrite this. You can rewrite this as a first order system, linear in chi. You just call the second order derivatives some other variable, and you have a matrix that it includes just first order system. So that essentially tells you that chi and some value lambda bar equals lambda bar 2 is linear. Let's call it m. And the value of chi at lambda bar equals lambda bar 1. Now this breaks down, so you can apply this between here and here, which is what I'm doing. What I'm doing here. The separation, fine parameter separation at some, between C0 and C1 at some point is just linearly related to the fine parameter separation between C0 and C1 at some other state. So this is a prescribed minus, in here it's a lower C. Where this is positive, this is negative, and so K2 for some K2 some constant. Now, you could say the same between here and here, but the problem is, in here, the fine parameter separator is infinite. So m is going to diverge infinite. So this will not apply between here and here.
Sorry. Does the K2 depends on something?
Yes.
It depends on what?
It depends on crazy things. We've gone through, this is the interior of the star. So it depends on the interior of the star. Depends on what matter you've got.
But this, the K2 has some evolution, right? It should change over time.
Well, what do you mean over time? I'm just giving you
over some parameter.
So I'm just saying that, so
because you can always take two real values and say they are proportional to each other.
sorry, you can do.
You can always take two numbers and say they are proportional to each other. If separation in different points, what do I expect the K2 to? How do I expect this factor to behave? Is there some?
So
If I take this separation, this proportional, this constant
yeah.
K2 along separation in different points, how do I expect the K2 to behave? Because, for example, K2 needs to be 0 when you get the separation on square plus, right? So K2 needs to go to 0 in square plus. For example,
Square minus one.
between square minus and square plus,
Yeah.
for example.
Well, in that case, it will be infinite.
Uh,
In that case, we just don't have a. Yeah, it will be infinite if you wish.
yeah, infinite
It's not really. They're not
inside,
linearly
zero on
related.
the
They're
other
not
side.
linearly related. That equation just wouldn't apply between square minus and square plus.
But if I take the affine parameter separation between two geodesics C and C prime along two constant V values, V and V prime, I don't know. Is the K2 between those guys related to V prime minus V or something like that?
So the K2 between these two lines, is that related to what?
If you take the affine parameter separation by two geodesics coming from square minus,
Okay. Like C is one.
yeah, there's one and another one.
Yeah.
Coming from V prime, for example.
Coming from?
From some value V prime.
Okay. This V prime. What's the?
Yeah, some other value between these guys.
Another value between these guys. So V prime.
Let V prime be bigger than V0, just for
V prime.
okay.
This one will just. This one is not coming back out to square plus. This one ends up at the same line.
Okay. Aren't you relating? Oh, you need to relate the.
V0 is the null generator of the horizon. It's the last one. The first one that can't escape.
You could just imagine that without a black hole you have two flashlights, for example, and then you make a flashlight to go, and then pass some time, and then another flashlight to go, and then you have a star, and it's collapsing. The one that is, and you can, for example, make the word line of these two flashlights, and you can always see like for some point they are just taken apart, because the first flashlight, that is when you already you don't have a black hole, for example, this flashlight will go to infinity, but the other one you push it exactly to be in the black hole horizon, so the flashlight will be just there. So the separation will be just increasing, because the one in the horizon will not go out, but the one that was before the flashlight to the black hole before will be the infinity. So that's what this is implying here. So basically, one is getting in the horizon of the black hole, the other is going to infinity. So the distance between them are going to infinity. That's what is happening there. That's why this is what this is implying, that before the black hole is in. And when we take whenever two different two different word lines for particles before the black hole is formed. You always can have this kind of thing. But if you take before those.
Okay, you need to use the C0. There's the last.
Yes.
The last one.
So the statement here is, this distance is linear in this. You double this distance. Okay, you want to take another geodesic instead of C0 and C1. Let's say that you take another geodesic before this one, before V1. So V2, let's call it V2, C2, V2. So you double this, and then this distance between C0 and C2 will be related in this way, will be 2 times K2. So I think in read this said and heuristically justified in many places. I haven't seen the details anywhere, I have to say, and looked for it. If you can find it, that would be great. Okay. Otherwise, we'll just stick with it. I mean, I've seen it in very rigorous places, so it must be correct. And heuristically, it kind of makes sense. So, and as I said, and you asked the question, what does K2 depend on? So K2 may depend on a lot of stuff. One of them is we're tracing null geodesics through the interior of a star. So the K2 will depend on the interior of the star. Now the magic about it all is that that will not make a difference at the end when it comes to Hawking radiation. At this stage it does. So okay, so now we can relate. So we already related the phi parameter here with the phi parameter here via this. And now we can relate the phi parameter here with the phi parameter here. And therefore we can relate the phi parameter separation here along chi minus with the phi parameter separation along chi plus. And that relationship is crucial. Finite phi parameter separation here will give you infinite phi parameter separation here. Growing exponentially as you get close to C0. And that's exactly what gives rise to thermal Hawking radiation. So far, I haven't shown that, but we have that U at V1 as the approach gets closer, as CZ1 gets close to C0, so as lambda goes to 0 from the left. So 4m is kappa minus 1, where kappa is the surface gravity. So that will be minus kappa 1 log lambda K1 from what we had. And now, well, this is as, so this is lambda 1 goes to 0. Lambda 1, yeah, this is as I said, as the geodesic C1 gets close to the geodesic C0. of the neighboring geodesics, the distance between the neighboring geodesic C0 and C1 gets to 0. And I'm getting C1, I'm letting C1 approach C0. This is, I'm using loose notation if you wish. Here the argument is V, here the argument is lambda, but it's, strictly speaking, it's wrong, but it's obviously, it's obvious what I mean. But I mean the value view that corresponds to V equals V1. So the value view along lambda, which corresponds to the point that, sorry, not along lambda, along C. The value view along C at the moment when C crosses C1. Okay? And that is given by the value of U when lambda is equal to lambda 1. Right? The value that we give at lambda. By definition of lambda 1. Okay, we've got this, and now we can use this relationship. And lambda 1 is V0 minus V1. K1 times K2. K1 and K2, they're both negative, so K1 times K2 is positive. Okay, so this is very important. This tells you, as I said, how the growth of U define parameter separation between C0 and C1 as C1 approaches C0 along scribe plus goes to infinity, in which way it tells you the asymptotic behavior of that happens. It goes to infinity exponentially, logarithmically as define parameter separation between C0 and C1 goes to 0 along scribe minus. Okay, so far just purely geometry. Okay, now let's put scalar field. A real and massless scalar field propagating on this spacetime. So we choose the Minkowski vacuum on scribe minus in the following way. Okay. So as I said, at the start you've got matter, or gas, if you wish, that starts collapsing, gravitationally collapsing. Now, we assume that it's so dispersed at t equals minus infinity at the early times, that at the early times it's just flat. Okay? So that's why I'm drawing flat spacetime asymptotically. So at early times, at t equals minus infinity, the collapsing matter so dispersed that the spacetime is approximately flat. And we can use scribe minus as a Cauchy surface remember, when I say Cauchy surface, strictly speaking, scribe minus is not a Cauchy surface because it has to be, Cauchy surface has to be space-like. I'm using loose notation, loose terminology, scribe minus as a Cauchy surface, meaning that you give initial data for the field, value of the field, at that surface, and the value of the normal derivative of the field, normal to that surface, and then you can evolve that data and you get the value of the field anywhere else to the future, okay, by a Kirchhoff integral that I gave at some stage. You use the reductive function to evolve that initial data. So in that sense, scribe minus is a Cauchy surface. If you start with anything in the future, anything anywhere else, and you trace it back to t equals minus infinity, you will have to cross scribe minus. Any causal word line trace back, you will have to cross scribe minus. Strictly speaking, scribe minus is a characteristic initial data surface. It's characteristic initial data because it's given in a null hypersurface. But as I say, I'll use terminology Cauchy surface with a slight abuse of notation. So we only need initial data, and again, initial is in quotes because it's not a t equals constant hypersurface on scribe minus for the fields. Okay, so it obeys the Klein-Gordon equation, where now the dot immersion is in the curve spacetime. And so you can use separation of variables. In Schwarzschild coordinates. Right. Well, first, if you wish, you can do a Fourier multi-composition, and then you can separate in. So you can use the staticity to separate to do a Fourier multi-composition, and you can use the spherical symmetry to decompose in spherical harmonics. So this Y's are the spherical harmonics. These N's are some normalization constants which we will choose so that the modes are normalized appropriately. And the A's are just the Fourier mode coefficients. What will become the annihilation and creation operators when we quantize. So they are normalized so that the integral over the sphere is this unit. There's different normalizations for the spherical harmonics, so that's a nightmare, but you have to choose whichever one you want to choose. You choose that one, and then in order to be consistent, just be consistent throughout the calculation. And these guys obey a radial equation. It obeys a Schrödinger right equation. So V is the potential. Let's given by this. This is just a scalar field propagating in Schwarzschild space. And this goes to 0 as either you go to infinity or you go to the horizon. So you know how to deal with this, at the very least from quantum mechanics. You've got a potential it doesn't have to peak at r equals 0, it peaks wherever. And it's just a Schrödinger right equation. You've got some wave coming in from infinity, part of the wave goes through with a transmission coefficient given by B, and part of the wave is refracted back with a reflection coefficient. So this is a reflection coefficient. And this is the transmission coefficient. So this is the backscattered part of the wave, the one that doesn't make it through the potential. Note, as omega becomes much larger than V, you can ignore V, and the solution of this is just a spherical wave, exponential of plus minus I omega star. So if you have this guy, if it works, if you ignore V, totally ignore V, then this would be an exact solution of an equation where you've ignored V, and so this would just transmit through. You would have no backscattered wave. So as omega becomes large, there's less of the wave gets backscattered, most of it just goes through the potential. You can impose the Vronsky condition, and that just gives you that the amplitude squared of sum of the backscatter part and the reflected part and the transmitted part is equal to unity if you've given, if you've normalized your incoming wave within amplitude. And for later on, what's going to be important is the so-called gray body factor, which is just this squared. It's called gamma L, the so-called gray body factor. Okay, so this is a second order linear ODE. There's no unique solution. You want to impose some boundary conditions and in order to get a unique solution. So, so that's one, imposing this will give you one particular unique solution, which is the so-called ingoing solution. So we define the E modes as, okay, I'll call all this phi Lm omega. So, with a particular choice, with a particular choice of this boundary condition, so that's purely ingoing wave and phi equals infinity, that gives you a unique solution of the radial translation, and that will give you a unique phi L omega. So that's as x go to square minus okay. So I've just asked
What is the in the NL omega? Is it's reading. Well,
I'm actually not including the A's in here. That's not going to include the A's. Sorry.
so this reading about NL omega.
A. Now we'll determine just in the usual way. So we've just asked for the radial solution to behave like this at R equals infinity. So phi in Lm omega are positive frequency modes with respect to V. V is the fine parameter along chi minus. With respect to the affine parameter V along chi minus. Now, that's true when omega is positive and there are negative frequency modes when omega is negative. Okay, now we have our Klein-Gordon, our scalar product that we derived already for field with car station. It's the Klein-Gordon scalar product.
Mark, just maybe a simple question. So that when you let the omega to be complex in general, this condition will be to the real part of omega or whatever.
Which condition?
This condition.
But this condition is just, this is a condition, this condition only makes sense. This condition only makes, I mean, I'm just defining this for, everything we're going to do is just for omega real, so this condition is for omega real. What you can do is, you know, you define your I mean, so you define them for real omega, and then yeah. So basically, So I think for imaginary of omega positive, you also do that for real omega. You know, for real omega, there's still the ingoing modes for real omega positive and imaginary omega. There's still the ingoing modes for imaginary omega positive. I don't know what your question was. If what still is the same?
I mean, the point was that how could I interpret this if I allow the omega to become complex? So if I let omega to be complex, so how much I would change this to make sense?
Yeah, I mean, you wouldn't call them positive frequency modes anymore. Right? So we're not, you know, we're only looking, because positive frequency just tells you. So if frequency is not, it's not real, it's not positive, then it just comes. So you wouldn't call them positive frequency modes. You can still define phi in, you know, in this way, to be given by this, even when omega is complex. So this is a boundary condition. This is a well-defined boundary. This is a true boundary condition for omega complex when imaginary omega is positive. When imaginary omega is negative, then it's not a good boundary condition. And it's just the way you say phi in, what you say that phi in is equal to whenever imaginary omega is negative, is just by analytic continuation from positive imaginary omega and zero imaginary omega. Okay, so that's about defining phi in and other solutions for complex omega. We're not going to bother about that And even in that case, if you can define phi in that way, you wouldn't really call them, you wouldn't call them positive frequency solutions. But there would be the analytic continuation in the complex frequency plane of what we call positive frequency solutions, of solutions which are positive frequency with respect to V when omega is real. I think I've made this more complicated than this, but okay, so I mean we're not going to let omega be complex. At least not for now, anyway. Okay, so we can now we want to normalize them. So the Klein-Gordon scalar product. So remember the expression that I gave. So in this case we want phi, so lambda, capital lambda